Welcome back. In this video, we're going to solve algebraic equations in one variable. We're going to start with some vocabulary. Equivalent equations. Equivalent equations are equations that have the same solution set over a given domain. And domain is simply the inputs or what you'll input for the variable or use for the variable. Transformations. Transformations are operations on an equation that produce a simpler or equivalent equation. So we transform equations in a variety of ways. Listed below, you can see here that we transform equations by substitution, by addition or subtraction, and by multiplication or division. So let's take a look at a sample here. We have the equation 2x plus 1 equals 10 plus 5. So if we wanted to transform this by substitution, we would replace an expression with an equivalent equation. Or with an equivalent expression. Well, we can simplify the 10 plus 5. So by substitution, we would replace 10 plus 5 with 15. So that's all substitution is generally just simplifying. But to solve this equation, we can also transform it by adding or subtracting. In this case, what we want to do is we want to get 2x on one side and we'll move the 1 to the other. So if we subtract 1 from both sides of the equation here, we'll do subtraction. That leaves us with 2x equals 14. So here now we have subtracted the same value, -1, from both sides of the equation. So we have our 2x equals 14, and we really want to find out what x is, and not 2 times x. So another transformation is you can multiply or divide, depending on what you have. I suppose if we had a fraction here, we would multiply, but we have the integer 2. We just divide by 2 and transform it again. Now, equations are like scales. They have to be in balance, okay? So what you do to one side of the equation, you must do to the other. So that's why when we subtracted or added, we subtracted 1 from both sides. And here we are going to divide both sides by 2. And by dividing by 2, we get 2 over 2 is 1, so we isolate x all by itself, and we get x equals 7. I suppose isolating x all by itself is a little redundant, but that's what we're doing. So here are some samples that we can do, and we'll work on doing some transformations. We have 3x plus 7 is equal to 4x plus 9. And we want to solve for x. We can subtract 3x from both sides of the equation. So 3x minus 3x is 0x. And you get 7 equals 4x minus 3x is just plain 1x equals plus 9. But we'd like to find x. And working down and trying to keep our equal signs in a row, we'll subtract 9 from the right side and 9 from the left side. And 7 minus 9, we get -2 equals x. Or if you prefer, x equals -2. Sample problem 2. We're going to apply the distributive property here. So we are going to simplify, going back to our notes. We're going to do some substitution, and we're going to say, okay, this becomes 6x minus 15 by distributing the 3 minus the quantity 5x plus 1 equals -3. So we're taking the opposite of this entire quantity, which means it's like multiplying the 5x and the 1 by -1. Okay, so that becomes minus 5x minus 1. We're taking the opposite of that entire quantity, equals negative 3. We can simplify 6x minus 5x and the negative 15 minus 1. So that could be x minus 16 equals negative 3. But we want to find out what x is. So we'll do another transformation. We will add 16 to the left side. Minus 16 plus 16 is 0. And of course then we have to add 16 to the right side. And we get x equals 13. Number 3, that's an easy one. We'll just divide both sides by 7. And x equals negative 6. Number 4, a little bit more challenging. Now we have a fraction. And we can do this in one step by using the property of the multiplicative inverse. Okay? Multiplicative inverse says that if we multiply something by its reciprocal, we get an output of 1. And that's what we want. We've always been getting a coefficient of 1 on our unknown, which happens to be x, each time. So we will apply the multiplicative inverse and multiply both sides by 7/3. And on the left side, 7/3 times 3/7 is just plain old 1x. And I will simplify the right side, and we get x equals 21. Number 5, we've seen this kind of problem before. I think I'll leave this one for you to work on, and you can bring that one to class. Make sure you write that down in your notes. Let's move on to writing phrases as expressions. You're going to see some work like this. So writing phrases as expressions, now a little bit more challenging word problem type things. So the sum of two numbers is 50. Looks like we have two different numbers. We could say that's like x plus y equals 50. Okay, but we really don't want to work in two variables right now. But that would be correct. One number is x and one number is y. So sure enough, one number is x. And it says write an expression representing the other number. Well, our other number, it happens to be y here. Okay? Well, the other number, y, we want to get y all by itself. So if I subtract x from both sides, and this is legal, we can do that. We've been doing that earlier. We get y equals 50 minus x. So our answer here is 50 minus x. If we have two numbers, if one of the numbers is x, the other number is 50 minus x. Moving on, some other information that you need is we need to take a look at what the algebraic representation of consecutive integers is. You may remember your integers are both positive and negative, like negative 3, negative 2, negative 1, 0, 1, 2, 3, and so on. Those are your integers. So consecutive integers, if we think about our number line, consecutive integers, 0 to 1 to 2. Well, how do we jump from 0 to 1? And how do we jump from 1 to 2? What do we do? Well, if we let x equal our first integer, no matter what it is, it could be 0, it could be negative 5, it could be 10, doesn't matter what our first integer is, how do we get to the next integer? Well, we have to add 1 to our first integer. So consecutive integers, we represent those as x, the first integer. The next integer would be x plus 1, and x plus 2, and so on. I suppose if you wanted to, you could go the other way. You could have x, and of course the one before x would be x minus 1. And 2 before that one would be x minus 2. So you could work in both directions if you really wanted to. Now consecutive even integers, Evens are numbers like 2, 4, 6, etc. Of course, we can go 0 and -2, -4. We can work in both directions. Well, with even integers, let's say 0 is even. To get from 0 to 2, we skip 1 and we go all the way to 2. And we skip 3 and we go all the way to 4. So if we'll let n equal our first integer, and I should call it even, our first even integer is n. Well, how do we get from our first integer to the next one? How do we get from 2 to 4? Well, we can't count by ones. We have to count by twos. So consecutive evens will be represented by n plus 2, n plus 4, and so on. And again, we could count backwards if we wanted to. If n is our first integer, the one before that would be n minus 2. The one before that would be n minus 4. Consecutive odd integers, I'm going to leave that one to you. See if you can figure that one out and bring that to class as well. And finally, let's take a look at a sample problem. If x is the first of 3 consecutive even integers, express their sum in terms of x. So what we want to do first is we want to identify our variable. Okay, and in fact, it's identified for us. X is the first of 3 consecutive even integers. That is really we have just defined x. So x equals the first even integer. Well, consecutive evens, we went by twos. So we had to skip the odd and go to the next even. So that's why n plus 2, n plus 4. So 3 consecutive evens, x plus 2, x plus 4, and we want the sum of those. So that is the sum of 3 consecutive even integers. And that is our introduction to solving equations and a little bit more. And we will see you in class.